Good evening, everyone. I wanted to look into the Selenelion Eclipse because while I felt it was revealing, I wanted to just tweak the rule just one small bit to make sure that I guarantee that it's 100% visible without refraction. So I've made a little bit of updates. This bottom one is the original, and I've made some small updates. So I've just changed the color on these particular bars. So the left side of the sun is going to be all red. The right side of the sun is all going to be blue. And as you can see here, you'll be able to see. So here's a reminder here. So red lines arriving from the left side of the sun, blue lines are arriving from the right-hand side of the sun. Okay, so as you can see, they're crossing over. The red's coming up and the blue's going down, and then they strike the planet. And I've just changed that a little bit so it's a bit more visible. And so I believe that the red ones were the one going up and the blue ones were the ones going down. So as you can see, the red is on the top side of the blue and the red's on the top side of blue. Blue's under red, blue's under red, right? So that's the two different pathways. So that's why this particular patch is darkest, because in here, light's still making it around the corner. That was all the, I made some updates in here. So this was the one where I was talking about. You can see it without refraction at 813 meters. Now, what I did here was I actually had it like dead straight in the center, right on the side. So that's the result that if you were exactly perpendicular to both the sun and the moon, you'd be 813 meters. And as you can see, it says 0.083 because every kilometer on this thing was 1 unit. So 813 meters. Now, I'll expand a little bit on this thing. So the observer moves 1 degree every 4 minutes. So if you're at 552, you're all the way down here, and you roll over to here by 556, and then you roll over to here by 6 a.m., roll over to there by 6:04 a.m., roll over to here by 6:08 a.m. So these guys on this side are going to see more sun because the sunrise is happening, whereas these guys will be able to see the moon for longer. And that's why most people who do the impossible eclipse, they're seeing the moon up high in the sky, and it is setting with time. And when it is setting, that's when the bottom part is becoming dark, right? So when the bottom part is becoming dark, that's when the Earth is blocking out the light, and the moon is traveling down according to the person, of course, into the observer, because the planet is rolling backwards. Okay, so they're rolling this way. I've noted this here. This is the strike point. That's where the particular line hits the edge of the surface. And so that's when it starts to accelerate up to the 813 meters, right? So that's the point where it hits the horizon. And that, according to this, is at 102 kilometers. So that's one thing I've just did. So the old one here has just been updated just a little bit. Now I figured I would look at this, and I was thinking, it's a great idea. I'll go out there and estimate all the moon's movements through time. And I thought, I'll just do the formula. I'll just be able to go out there and move it. But then I started to laboriously put times in here. I thought, I can't be stopped. It's just too many bloody time blocks. So what I tried to do here, so I just did a quick Google search, didn't even care for accuracy, right? And I went for a moon orbit. It said 27.3 days. I divided that down to 655 hours, or a moon orbit of 39,312 minutes. So it should take 39,000 minutes for the moon to go around the planet, right? Now I divided by 4 to be able to go and get my 4-minute intervals, which is basically where we move 1 degree on the planet, and I got a result 98.28, right? So I used the 360 degree orbit, and I and I did the maths. So 360 divided by 98.28, I got a degree change of 0.0366 for every minute when it is spinning. Now, of course, we are spinning too, so it's like you got a combination of numbers going on here all the time. So I've done a sort of digital representation of what that might look like. So the penumbra and umbra are still here. You know, this is the center of the moon. So when these lines strike, that's the center of the moon. So we're looking at 3:48 a.m. Rolling through to what looks like about 4:50ish when it enters the umbra, and I've just picked a random at 6 a.m. datum here, and as you can see here, it looks like it's the width of the moon, is about 5:33ish to about 6:27. So I did that, just estimated there. So the estimate of the moon's width seems to be about 54 minutes according to my settings. Right? I mean, obviously, I'm not entirely saying that this is exactly accurate, but according to this thing, 54 minutes is what I get. And up here, I went out there and estimated, the center point, and then I add 27 minutes for each side because I've got one half of the moon on one side and one half of the moon on the other side. And I estimated that it would exit the penumbra and enter the penumbra in about 5 hours and 14 minutes. Now, when I look online, we got the kilometers per hour. I'll get back to that one. So according to this, when I looked at this, 4 a.m. to 10 a.m., that's about 6 hours. So their estimates are it's going to take longer. So I'm faster according to that. This one here was 3,683 kilometers per hour is the moon's orbit speed. So my moon's orbit speed, when I go out there and I get a distance from, let's say, 5 a.m. to 6 a.m., I get 3,822 kilometers, right? So that's over 1 hour. My moon seems to be traveling about 3,822 kilometers. So look, this is rough numbers, and they're coming out kind of close. I mean, obviously they're not the same, but I mean, it's my drawing versus these guys who have got 3D modeling programs, whereas I'm just simply drawing this on lines. This is just 2D. So I'm happy with this, but I didn't want to have to explore this anymore because the amount of lines I drew was bloody painful. What I wanted to look at was this new diagram. So on this new diagram, as you can see here, I'll turn the pink off for a second. Okay, on this new diagram, the red's on the left hand side of the sun, and the blue is on the right hand side of the sun. Same sort of thing. All right, so we're all in agreement of this penumbra and umbra is considered exactly the same. So what I'm going to do is I'm going to turn off the umbra and penumbra, and I'm going to show the pink line again. Now, on this, the reason why I decided to change this particular diagram was I figured what I will do is I will strike it to the bottom of the moon, right? So this pink line goes to the bottom of the moon on this particular instance, and that comes all the way up to, some point on the planet, and will strike the horizon, and it will extend up to an observer, right? And I did the same thing for the sun. So let me just zoom out. So I did the bottom side of the sun. So what I wanted to do is I wanted to guarantee that I had the entire disk within view for the observer. So the entire disk of the sun and the entire disk of the moon is visible 100% without refraction, right? And it actually gave me the opportunity to be able to have an observer which was slightly closer to the moon side. So instead of it being 813 meters right here, I don't know what that one is. That one probably shouldn't even be there. I don't know. Doesn't seem right to me. I think that's for carryover. So yeah, so I had 813 meters here. So when I strike this point here to this strike point, and when I strike the sun to this strike point, which is where it's supposed to hit, it puts my observer closer to the moon. And believe it or not, I get an observer height of 500 meters this time round. So actually having it closer to the moon and having the equal balance of strike points, the observer can be closer to the moon side and can be 500 meters high, right? And so the reason why I can confirm the strike point heights here, right, is, as you can see here, this is 79.7 kilometers to the strike point to the observer height, and on the left hand side 79.798 from the strike height to the observer height. So we know that those are equal, right? So that is an equal distance to look to the left and an equal distance to look to the right for the observer to have vision of something to the two strike points, which is the horizon line, to the bottom of the sun and to the bottom of the moon. So we know that that is equal and balanced. And so yeah, 500 meters. So if you get yourself in the right position, which I couldn't be honest, I couldn't even tell you how to get into the right place. But if someone is lucky enough to be in a position which is, according to this, 0.45 degrees from the perpendicular point, so 0.5, so about 2 minutes. 2 minutes before they reach the parallel point, before they reach perpendicular point, sorry. So about 2 minutes in distance, you'll be 500 meters high, and you'll be able to see the entire disk of the sun and the entire disk of the moon above your horizon line, without refraction included. So there you go. 500 meters. It's far easier than you think. All right, thanks for listening.